Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on three-phase AC circuits. By solving these problems, we shall learn how to compute apparent power, active power and reactive power for three-phase balanced star-connected loads. For balanced three-phase load, total apparent power S equals to 3 times V phase into I phase, where V phase is the phase voltage and I phase is the phase current. Total active power P equals to 3 times V phase into I phase cos phi, where cos phi is the load power factor. P may be expressed as S into cos phi. Total reactive power Q equals to 3 times V phase into I phase sin phi, that is equal to S into sin phi. For balanced three-phase star-connected load, line voltage VL equals to root 3 times V phase, where V phase is the phase voltage. Line current IL equals to phase current I phase. Now we can write apparent power S equals to root 3 times VL into IL. Active power P equals to root 3 times VL into IL cos phi, and reactive power Q equals to root 3 times VL into IL sin phi. A three-phase voltage source has a phase voltage of 120 volts and supplies star-connected load having impedance 36 plus J48 ohm per phase. We have to calculate the line voltage, the line current, the power factor and the total power supplied to the load. Let us first write down the given data. Terminal voltage per phase, V phase equals to 120 volts. Since the load is star connected, line to line terminal voltage VL equals to root 3 times V phase, that is equal to root 3 into 120, that gives us 207.8461 volts. Impedance per phase Z equals to 36 plus J48 ohm. This may be written in polar form as 60 ohm at an angle 53.1301 degree. For star connected load, line current IL equals to phase current I phase, that is equal to V phase divided by Z. Using values we get 120 divided by 60, that gives us 2 ampere. Power factor of the load cos phi equals to cos of 53.1301 degree, that is equal to 0.6 lagging. Total power supplied to the load P equals to root 3 times VL into IL cos phi. Using values we get root 3 into 207.8461 into 2 into 0.6, that gives us 432 watts. A 400 volts 50 Hz AC supply is applied to three star-connected identical impedances, each consisting of a 40 ohm resistance in series with 30 ohm inductive reactance. We have to calculate line current, power factor and total power supplied. Let us first write down the given data. Line to line terminal voltage VL equals to 400 volts. Since the load is star connected, terminal voltage per phase V phase equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.9401 volts. Resistance per phase R equals to 40 ohm. Inductive reactance per phase XL equals to 30 ohm. Let us now calculate impedance per phase. Z equals to R plus JXL, that is equal to 40 plus J30 ohm. This may be written in polar form as 50 ohm at an angle 36.8699 degree. For star connected load, line current IL equals to phase current I phase, that is equal to V phase divided by Z. Using values we get 230.9401 divided by 50, that gives us 4.6188 ampere. Now we shall calculate load power factor. Cos phi equals to cos of 36.8699 degree, that gives us 0.8. Lagging. Total power supplied P equals to root 3 times VLIL cos phi. Using values we get root 3 into 400 into 4.6188 into 0.8, that gives us 2560 watts. A balanced star connected load of 8 plus J6 ohm per phase is connected to a 3-phase 230 volt 50 Hz AC supply. We have to calculate the line current, power factor, active, reactive and apparent powers. Let us first write down the given data. Line to line terminal voltage VL equals to 230 volts. Since the load is star connected, terminal voltage per phase V phase equals to VL by root 3, that is equal to 230 divided by root 3, that gives us 132.79 volts. Impedance per phase Z equals to 8 plus J6 ohm. This may be written in polar form as 10 ohm at an angle 36.8699 degree. For star connected load, line current IL equals to phase current I phase, that is equal to V phase divided by Z. Using values we get 132.79 divided by 10, that gives us 13.279 ampere. Let us determine power factor of the load. Cos phi equals to cos of 36.8699 degree, that is equal to 0.8 lagging, and sin phi equals to sin of 36.8699 degree, that is equal to 0.6. Expression for apparent power for 3-phase load. S equals to root 3 times VL into IL. Using values we get root 3 into 230 into 13.279, that gives us 5290 volt amperes. Let us draw the power triangle for inductive load. From this triangle we get active power P equals to S into cos phi. Using values we get 5290 into 0.8, that gives us 4232 watts. And reactive power QL equals to S into sin phi. Using values we get 5290 into 0.6, that gives us 3174 volt ampere reactive. A balanced star-connected load of 2.5 ohm resistance and 0.03 Henry inductance in series in each phase is connected across a three-phase 415 volt 50 Hz AC supply. We have to compute line current, power factor, power input, kilovolt ampere and kilovolt ampere reactive taken by the load. Let us first write down the given data. Line to line terminal voltage VL equals to 415 volts. For balanced star-connected load, terminal voltage per phase V phase equals to VL by root 3, that is equal to 415 divided by root 3, that gives us 239.6 volts. Supply frequency F equals to 50 Hz. Resistance per phase R equals to 2.5 ohm. Inductance per phase L equals to 0.03 Henry. Let us first compute inductive reactance per phase. XL equals to 2 pi F into L. Using values we get 2 pi into 50 into 0.03. That gives us 9.425 ohm. Now we shall write down impedance per phase in phasor form. Z equals to R plus JXL, that is equal to 2.5 plus J 9.425 ohm. This may be written in polar form as 9.751 ohm at an angle 75.1443 degree. For balanced star-connected load, line current IL equals to phase current I phase, that is equal to V phase divided by Z. Using values we get 239.6 divided by 9.751, that is equal to 24.572 ampere. Power factor cos phi equals to cos of 75.1443 degree, that is equal to 0.2564 lagging. For three-phase balanced load, apparent power S equals to root 3 times VL into IL. Using values we get root 3 into 415 into 24.572, that gives us 17,662.38 volt ampere or 17.66238 kilovolt ampere. Let us draw the power triangle for inductive load. From this triangle we get input power P equals to S into cos phi. Using values we get 17.66238 into 0.2564, that is equal to 4.53 kilowatt, and reactive power UL equals to S into sin phi. Using values we get 17.66238 into sine of 75.1443 degree, that is equal to 17.072 kilovolt ampere reactive. Each phase of a star-connected load comprises of a non-reactive resistance of 10 ohm in parallel with a capacitance of 320 microfarad. We have to calculate the line current, the power absorbed, the total kilovolt ampere and the power factor when connected to a 400 volt 3-phase 50 Hz power supply. Let us first write down the given data. Line to line terminal voltage VL equals to 400 volts. For balanced star connected load, terminal voltage per phase, V phase equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.9401 volts. Supply frequency F equals to 50 Hz. Resistance per phase R equals to 10 ohm. Let us first compute conductance per phase. G equals to 1 upon R, that is equal to 1 upon 10, that gives us 0.1 mho. Given capacitance per phase C equals to 320 microfarad, that is equal to 320 into 10 to the power minus 6 farad. Let us now compute capacitive susceptance per phase. Bc equals to 2 pi f into C. Using values we get 2 pi into 50 into 320 into 10 to the power minus 6, that is equal to 0.1005 mho. Now we shall write down admittance per phase in phasor form. Y equals to G plus JBC, that is equal to 0.1 plus J, 0.1005 mho. This may be written in polar form as 0.1418 mho at an angle 45.1517 degree. For balanced star connected load, line current IL equals to phase current I phase, that is equal to V phase into Y. Using values we get 230.9401 into 0.1418, that gives us 32.7467 ampere. Let us now compute power factor. Cos phi equals to cos of 45.1517 degree, that is equal to 0.7052, leading. For balanced three-phase load, apparent power S equals to root 3 times VL into IL. Using values we get root 3 into 400 into 32.7467, that gives us 22,688 volt ampere or 22.688 kilovolt ampere. Power absorbed P equals to S into cos phi. Using values we get 22.688 into 0.7052, that gives us 16 kilowatt. So today we have solved a couple of numerical problems on three-phase AC circuits. By solving these problems, we have learned how to compute apparent power, active power, and reactive power for three-phase balanced star-connected loads. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.